Hello, colleagues. Today we are going to listen to Boris Ivanovic from NVIDIA, and Boris is a senior research scientist. I hope that Boris is correct pronunciation. Not Boris, or Boris.
You know better.
Yeah, just in Russia it's Boris. Boris. In managing NVIDIA's autonomous vehicle research group. His research interests include novel end-to-end AV architectures, sensor and traffic simulation, AI safety, and the thoughtful integration of foundational models in AV development. Prior to joining NVIDIA, he received his Ph.D. in Aeronautics and Astronautics under the supervision of Marco Pavone in 2021 and an MS in Computer Science in 2018, both from Stanford University. And he received his B.A.Sc in Engineering Science from the University of Toronto in 2016. So, Boris, please start. Yeah, I'm sorry about that.
No, it's no problem at all. Like I said, you probably have the better pronunciation. So yeah, hi everyone here and on the call. It's great to be here. So yeah, today, as Alex said, I'm going to be talking about kind of architecting next generation AV stacks. And in particular, I say next generation because right now, there's quite a large revolution going on in the AV domain. And typically, when I say here a large revolution, I'm referring to, on the one hand, we have kind of a large shift from traditional modular AV architectures, where you have a cascade of different task-specific modules, towards a little bit more learning-based, end-to-end kind of architecture. And, you know, as part of this big shift, I shouldn't say that it's actually, you know, just from one or the other. It's actually, there's kind of a spectrum here along the way in which you can kind of choose, okay, which components should be learned, which components should not. Are you able to pass gradients? Are you able to use those gradients, and et cetera? And so one of these kind of big revolutions that we've been looking at in our group, but of course, you probably see here at Nuro and elsewhere, is this shift towards leveraging differentiability, but retaining modularity as well, to retain interpretability and, you know, ease debugging and et cetera. So this is one kind of big direction that I think the field has been moving in for at least the past few years. But along with this revolution, you also need innovation in infrastructure to actually train such a model, to get data, to, you know, test it in closed loop and evaluate, you know, in a safe manner, for example. And actually today I'm going to be talking about both of these directions on the architectural side and then also on the infrastructural side. And in particular, we'll be looking at some of you know, world representation methods that we've developed very recently and how we can maybe use those to help with these evaluating and training these models. So broadly, today what I'm going to talk about is, so as I mentioned, some of our recent explorations into end-to-end driving architectures, and then world representations, but focusing in particular on dynamic scene reconstruction and seeing what you can do from that. I'm gonna have to excuse the choppy videos. They look lovely there, but over the internet back and forth, it's going to be a little bit choppy. So without further ado, let's start with the first topic, which is exploring the design space of end-to-end driving architectures. So as I'm sure you're aware here, even if I wanted to implement some model that's end-to-end and has modules, but they're still differentiable, I haven't really solved the problem, right? There's still quite a lot of choices I can make here in what kinds of modules I'm using. So, if I'm doing something like, if I want to try and understand, okay, how shall I best represent the world? Should I do something like a dense representation, like a semantic occupancy grid? Or should I do something like, just trying to detect specific objects and then predicting where they go in the future, which is a little bit more, let's say, sparse representation of the world. And these, I shouldn't say there's kind of one obvious choice or the other. I mean, just last year, both of these kinds of approaches were espoused in state-of-the-art research. One from I'm showing here ICCV and one from CDPR, actually the best paper at CDPR. Now, that's just one choice, is what kind of module do you even want to do here? But even if you do, then let's say make a choice like this, then there's still a question of, okay, what representation of information are you passing between modules, right? Even if you know that you need to do mapping online, okay, are you going to pass in a dense semantic bird's eye view grid of a map, or are you going to just regress vectorized polylines and polygons and use that to, feed into your downstream model? That's an open question. And even, this is kind of one question of just what should you output, but then there's another question of what should you actually take into, for example, motion planning downstream. Should you take in, a little bit more interpretable, these rasterized grids or painting the bounding boxes and treating everything like an image, or should you go a little bit more to the featureized space, where now you're just passing in, for example, transformer queries from upstream models towards your downstream components. And all of this is actually compounded by the fact that there's also, you still have a choice in where you're actually placing these modules. When I say placement here, it's basically which, the outputs of which module go into which other module. And this only just adds to actually the complexity of the entire problem in actually selecting and building a network of choice. Now, in order to actually, for us even help systematically understand, the impact of some of these choices and actually give us a way to explore the design space in a way that's not just kind of random guessing, we basically came up, we kind of defined 3 key dimensions along which you might make decisions. And they relate to, that kind of cycle I showed, the choices I discussed before. The first is necessity. So which tasks or modules are actually essential for what you want to do? And is there any redundancy? I think this is kind of still an open question here. The second is placement. So I mentioned, even if you've selected the modules that you want to implement, how should they be arranged? Should you have, should you follow that cascaded idea of passing information from one to the other? Or should you do something where maybe, you have one feature being used in multiple modules and then, combine later? Or maybe a hybrid of these. And then finally, there's that question of representation. Should we do something like interpretable features? Should we do latent features? Should we do both? Should we do, something something different? And just to kind of show how actually even, in modern stacks, there's a lot of variance. And if I kind of plot some of these different recent works from last year on kind of the, let's call it with the same, graphical visualization, you can see that there's quite a lot of different choices made by different models, and they all roughly perform. I mean, I'm sure some perform better than the others in different axes, but they all roughly will, perform at a state-of-the-art level. So, how can we actually explore this space? How can we disambiguate maybe the choices and which ones matter? And so, a recent work that we've been working on in the group is actually to come up with a flexible computational driving graph that allows us to basically pick and choose and experiment with which modules matter, which decisions between the connectivity of them, which representations between them matter. And it allows us to do this in a flexible manner, which is extremely important if you're going to try and do a little bit of like architecture search here. I mean, effectively, that's what it is. And the best part is, so I mean, we describe all of this in a paper which will be very soon coming out on archive, but we're also going to be releasing the code. So even, if you want to do your own kind of architectural explorations, you can also take a look at this framework and try things out yourself. Now, when we actually set out to do this project, we figured, okay, we're going to, be exploring some different architecture choices, but we have to find a way to compare them. And so, unfortunately, for end-to-end driving, I don't know that I would be able to point out one consistent metric or one consistent evaluation framework that's used by multiple different works recently. And so, especially in for closed loop, I don't think I've seen any. But there is a consistent theme, at least, that, okay, well, open loop evaluation metrics are very easy to implement. And so typically what you'll find in a lot of state-of-the-art works is it'll be taking the Nucian's data set, which is, the classic one from 2019 from now called Motional, and basically performing effectively trajectory prediction on the ego vehicle, which is kind of open loop planning. That's the term used. And so we, we'll take this most common evaluation setup, at least for now, and we'll add a few other metrics in order to not just evaluate the, let's say, accuracy of this open loop prediction and rollout, but understanding the collision rate, for example, how much your model actually pays attention to other vehicles, and how much your model actually pays attention to the map. So we have also some map compliance metrics, which is effectively the percentage of time that you are driving off-road or off-lane, for example. And we've also made a few choices to standardize the actual lower level evaluation of these things. So in different papers, you'll find different choices, and that can make it a little bit difficult to compare, at least just by looking at the tables in the papers. And so the kind of few core decisions that we made to standardize everything is that, we're going to include vehicles and pedestrians in collision rates, not just one, not just the other. We're going to also evaluate the prediction accuracy with agents that have just partial features. We're not going to remove those from our evaluation set. And we're going to ensure at least 2 frames of input. There are some models that require velocities and accelerations, and so that's fine. We'll give them that information, and any more is kind of optional. So with this evaluation framework in mind, we basically set out to re-implement some of the common methods that we've seen in literature. Again, these are all, so UniAD, VAD, and ADMLP, these are all methods from roughly last year, roughly 2023. And if you take a look at the full nuisance validation set, which very closely matches what a lot of these papers themselves were looking at, you see, I would argue, you see kind of a consistent story, right? You see, one method is then bested by another, is bested by another, and it's kind of, okay, this one was released later, and so they improved upon the other one, this one was released later, and et cetera. The same thing with, prediction accuracy of the trajectory with respect to the ground truth. Kind of seems like a consistent story. And then a little bit weird here, right? We see kind of the off-road rate or off-lane rates are a little bit actually not improving between these different models. But that's actually a little bit, it makes sense if you look at some of the deeper architectural choices, because some of these models, they actually don't look at the map itself. And so, okay, it makes sense, right? That they're gonna not necessarily care about the map. Now, the one thing that I'm sure you guys are intimately aware of is that if you just take a look at overall distribution of driving data, 95% of it is going to be driving straight with nothing around you, right? Unfortunately, that's the exact same distribution that you'll find in a lot of driving data sets that are released publicly, and the nuisance data set is not a stranger to this. So if we instead take a look at all of the driving scenarios that are not just driving straight, then actually it starts to get a little bit interesting in terms of the performance. The story is not as clear anymore, right? So here now we actually see, quite significant differences in collision rates between these different models. And, now, I mean, sure, maybe one is better than the other marginally, but they're starting to kind of look very similar here. And so, when we were hoping just to see, easy story to tell, and okay, we can use these inferences for ourselves, and we know the reasons. But here was there was still a little bit left for us to understand in some of these choices here. So the way that we set out to explore the design space here was, we'll say, okay, let's start at UniAD. UniAD method released last year, published at CVPR. I believe it won the best paper at CVPR. And we chose it as a starting place because it had quite a lot of actually already implemented, connections between different modules, and it already had a lot of implemented modules. So, okay, this is a good base for us to start from, and then we can kind of build or remove and explore from here. And in particular, just to make sure that all this terminology is clear, I'm basically just, the colors are denoting the type of representation that's going between modules, and then, there's a dotted line here for basically something that you don't do during training, but you only do during planning. Now, what's interesting is if we actually remove, so these grayed out edges are present in UniAD. They are actually part of the default architecture. But what's interesting is if you actually remove these edges, the model performs quite a bit. The model improves in performance quite a bit. And so, and actually it's quite significant. The collision rate reduces by, 2/3, and the accuracy improves by a third in percentage. And the reason for this is that, on the one hand, what they do is they pass queries, the transformer queries, from mapping to, to motion prediction. But what's interesting is these queries are actually quite noisy. And so it's actually harming, this module, which then harms downstream performance. And then if you remove this test time optimization that they do in order to generate motion plans, you also improve performance because during training, this optimization is not performed. The model does not know about this. And so at test time, you're adding something that the model was not originally trained with, and you actually end up harming performance. And then we said, okay, let's now analyze every other of these edges here in this architecture. And what's interesting is that basically, if you mess with any of these other edges, basically not much happens, not much changes in terms of the model performance. And we kind of found interestingly that if you add, even if you say, okay, but this is important and this is important between mapping and prediction and this occupancy prediction and planning, this is important. I want to add it back, but maybe I want to change my representation. Maybe I don't want to use latent feature, queries. I want to use explicit features. Still decreases performance. That noise is still there. And so, okay, this was kind of interesting for us, where we saw that a lot of these edges don't really matter too much if you just look at his downstream performance metric. And so we figured, okay, let's keep analyzing, is there maybe some redundancy, right? Let's look at some of the bigger choices you can make in terms of having these modules or not. And what we found was, actually, if you have quite related tasks, occupancy prediction and motion prediction, where motion prediction here I'm referring to if you have bounding boxes and you are predicting like the kind of from that sparse representation, whereas occupancy is a little bit more this, let's call it dense representation, where you're predicting, for every let's say pixel in your grid. What's interesting is these are actually redundant tasks. You can remove one and keep the other, or vice versa, and your performance will stay the same. And so, but what's very interesting is so most importantly, they also directly influence planning. If you remove this direct influence on planning, and you effectively just have planning coming from bird's eye view features, then both of these are critical to performance. And so actually this gave us a cue that, these two tasks, even if they don't directly influence planning, they really help in shaping the latent space of your bird's eye view, these original bird's eye view features that are coming from your multi-camera perception. Okay, this was kind of interesting. And what we basically, after a little bit more exploration and keeping these insights in mind, we basically settled on coming up with a new end-to-end AV architecture that's actually fully parallel. And what we mean by parallel is the only connections, you kind of have like it almost looks like a one-layer, network where you start from these bird's eye view features that you're getting from your multi-camera perception. And then each of these different tasks, mapping, motion prediction, occupancy prediction, and motion planning, basically serve as, let's call them representation formers. You're basically just learning an excellent latent space where you really only care about motion planning, but all of this needs to be, you need to know about this when you're actually making motion plans. And so, effectively, we found that if you just learn a strong representation via auxiliary tasks, at runtime, you don't need to use any of these, right? Just by going from bird's eye view features to planning, you're already, greatly outperforming some of these other methods, or at least performing similarly. And you're actually even, better respecting the map, which is kind of interesting because, again, we're not directly, explicitly using the map in planning. Now, the other benefit of this, besides, let's say, maintaining performance, is that without some of these other tasks running online, your runtime is significantly improved, right? And we were able to find that, in this, if you have this architecture and remove some of these, what we call auxiliary tasks, you're basically able to get, like a 1.5 to 2.5 to 3 times, speed up compared to existing state-of-the-art end-to-end approaches. And as another corollary, actually the performance of each of these sub-tasks is still maintained or even slightly better. than UniAD or some of these other end-to-end architectures. So, and I mean, this is kind of the classic image that, or the classic video that you see in a lot of these end-to-end papers where, this is kind of what it looks like when the model is running, where you have kind of the 6 cameras surrounding the vehicle, and then this is the bird's eye view representation that the model, this is what happens if you take a look at the mapping output and then you have your prediction and other heads, if you take a look at analyzing those. And this even, works quite well at nighttime. Now, the most visceral comparison of performance here, I think, is actually to just see, I mean, I wish it would show better here, but this speed difference is really something powerful. So for those of you in the room, I'm going to just show you here on my screen, right? This is what, like a visceral 4 times speed improvement looks like. And there's a lot of corollaries that come with that, because when you have higher replanning, right, you can maybe account for more, you can make other decisions, other determinations of how you architect your stack, you can think differently about safety, and et cetera, et cetera. But I just want to say that, this is, as a result of kind of this exploration through the architecture space, we kind of found that at least if you just look at kind of the performance metric that people care about, you can actually get there with a much simpler architecture and a much faster architecture. Of course, caveats are that this is all open with performance, right? You shouldn't take a look at this and say, this is, of course, transferable to real world driving, which is closed loop. So we're actually actively working on basically verifying if these conclusions hold when you do indeed bring such an architecture into the closed loop space. So keep an eye out for updates along that front. Now, are there any questions before I move on to the second topic here?
So this slight question from my side. You talked, there is no established benchmark, right? Is it right now there is an approach from Waymo using its Waymax? What do you think about it?
Waymax is a simulator, right? But Waymax does not implement, as best as I understand, the kinds of intelligent agents or reactive agents that you would need to, let's say, best match what reality looks like. So Waymax is an excellent platform for a simulator. Excellent, right? It's accelerated data, parallel and all that. But there are other pieces that you would want to add, especially also on the lines, for example, of sensor rendering and getting also that kind of information. So it's great if you want to evaluate, I would say, kind of post-perception. I think it's fantastic. But with everything now in the mix, now you need to start looking also at sensor simulation and intelligent agents as well. One of which I'll actually just talk about in the next section.
A quick question. So for these experiments, did you keep the same BEV backbone, I guess, as UniAD? Okay, so you didn't have to increase its capacity or anything? Exactly correct.
Yeah, we actually purposely didn't want to touch that. We just wanted to see, from the kind of, hopefully good backbone that's already there, how can you best use that information?
That's really the same as I wonder how much of this is it's scooting back work into the backbone that wouldn't do otherwise. So I'm also surprised of that. So maybe it's just easier to learn a representation that way.
Yeah, I mean, and also I think for me, the one thing that I was also latched onto was these kinds of bird's eye view representations. I mean, you have quite a lot of information, right? Depending on the spatial size that you care about, it could be something like, I don't know, 200 by 100 by 256, let's say, feature dimension. That's a huge amount of information, right? And so, I think it's kind of like, as you pointed out, right, a little bit by bringing some of the problem back, you're kind of forcing more, use of all of these, large feature vectors that are already in the bird's eye view grid. At least that's my hypothesis here. Okay, so on the next topic, so like I said, there's kind of an innovation or revolution here in the architectural space, also in the infrastructural space. So in this, what we, one of the core problems that you run into when you want to do simulation, especially simulation of a dynamic scene, if you want to test your vehicle, is you kind of have two things that you either run into. One is that you want to, let's say you want to, fully simulate everything with excellent amounts of 3D assets and everything. Okay, now you're going to need some artists to go through and place, recreate a beautiful world which matches something here, and then drive within it. Or you have tons of real data, and it's like, okay, let's use this real data to try and create some world, but then, we have to do dynamic scene reconstruction. And that's a very difficult open problem, at least in computer vision. And so, you're kind of faced with this problem right from the outset of how can you actually do, a really high fidelity sensor simulation, and, actually use it to test your vehicle. And so this base question is one that we want to focus on in the group, which is, if we have a driving log that contains posed RGB images and LiDAR, can we actually accurately reconstruct and represent the scene, and most importantly, including the dynamic objects that are in the scene? And the reason that I say including dynamic objects here is because I think over the past 2 years, or maybe 3 years, we've seen really a huge explosion in the computer vision community of methods like neural radiance fields, or NeRFs, which are absolutely fantastic at modeling and rendering static scenarios. And I'm showing here a video, this was from, 2 years ago, from Waymo, it's the block NeRF for it, where they reconstructed, multiple blocks of the San Francisco, parts of the San Francisco city. And what you can see is, even in this kind of choppy video, you can see that there are these kind of like black patches on the sides of the roads, these kinds of things. And what those are is basically the shadows of vehicles, dynamic vehicles that were removed in order to ensure that the NeRF can actually represent and reconstruct a static scene. And you need to do this because NeRF has an internal assumption of multi-view consistency and dynamic objects that breaks. So the core question here is, can we leverage this very high fidelity, strong NeRF-based representation and actually also model dynamic objects without requiring ground truth annotations to actually get bounding boxes and then remove them from the scene? And so, yes, we can. And this is the result of our latest work actually accepted to iClear called EmberNeRF. So what EmberNeRF is it is a NeRF-based approach to representing the world. And I'm going to kind of build up to the final model, where it starts just like any other NeRF. We are representing the static world by a neural radiance field. In this case, we're using instant NGP-based multi-resolution hash grids to represent the world in a very accurate and high-fidelity manner. And what this allows you to do is, you can take your XYZ position in the 3D world, as well as a viewing direction, query your neural radiance field, and get a color and density value back, which you can use to do volumetric rendering and get an image of the scenario. So great. And then the way that we train this is we render, we can compute pixel-wise reconstruction losses, and backpropagate everything. Great. But this is just static. So okay, let's now try and tackle the problem by just adding one more neural radiance field. Let's now add another NeRF, which takes now a 4D input, not just XYZ, but also the time, which frame you are trying to render. And then, just like the static field, this will give you color and density. And the hope is that by having this time parameter here, these two fields will learn to disambiguate. They'll learn to disentangle the scene. And one will hopefully model static scenarios, one will hopefully model dynamic scenarios, dynamic elements of the scenario. And when we first tried this, it kind of worked, right? You got a lot. The problem is you had a crazy amount of flickering between frames. And that's because this dynamic field never had to care about having consistent information across frames. It was effectively just memorizing each frame one by one. And so we saw tons of artifacts, and it was like, okay, well, now we have to think a little bit. And after a good amount of exploration, we finally settled on requiring one final component, which was actually managed to model flow. And the way that we do this is by, rather than just having the dynamic field, trying to remember each single frame by frame, we actually forced it to take the average of the information in the next frame and previous frame and use that with its current frame. And when I say take the information, this is what this flow field was actually tasked with doing. It was tasked with outputting, sometimes it's called optical flow in computer vision, but here it's kind of the scene flow. It's the 4D the change over time. And when you now factor this in, now we have really strong, this was actually really the key. This kind of emergent property of modeling flow was really the key to unlocking really strong reconstruction performance. And actually, these two videos that I'm showing here, I know they're small, but I'm going to show some larger ones. They're virtually identical. And that's actually the result of this reconstruction. And most importantly, in all, this entire process, there are 0 labels. There's nothing that we had to put in here. It's all completely from self-supervision, from reconstructing the original signals. And, what this allows you to do is, you can do many NERF-like things, which is, simply re-rendering your original input views and kind of seeing, okay, they match up well, great. But because this is also a 3D and 4D representation, you can also do resimulation of sensor data. So here we can actually simulate LiDAR, or we can densify LiDAR, or we can sparsify LiDAR, even in the exact same scenario, and see what happens if you had a different set of sensors. And perhaps most importantly, we can actually decompose the scene into its constituent components. So this is kind of, I would say the real nugget here is I can visualize these fields independently. I can render these fields independently. And so here's the static component. And then here you can see it's very crisply segmented out dynamic objects. Again, with no labels at all, just from this aggregation of information and self-supervision. And so those two were just the static and dynamic, and here I'm also visualizing the flow information, which is basically the motion, at least when you render it in 2D, is the motion of these pixels. But we can also view this in 3D and even in 4D. So we have kind of on the website of this model, which you can find at the bottom right, we actually have these visualizations running, and you can kind of move a slider along and see how we resimulate LiDAR compared to the ground truth information. And then something else that you can quite commonly do with NERFs is something called novel view synthesis, which is basically here we can freeze time and move our camera around in space. But something else that you can do when you have this 4D representation is you can freeze space and move time. And so on the right here, so I'm showing here this moving spatially, but on the right, after this sequence, we freeze the camera and then just let the world kind of just drive away, following where the actual ego vehicle was collecting data and went. Just quite interesting, and not something you can do if you just have spatial NERF. Now, this is all great, and we were very happy seeing these results. But so far, we've only been reconstructing the RGB, like our losses were only on the reconstruction of the RGB frame. And okay, that's great, but what about other information, right? What about if we task the model to actually distill and have a sense of other kinds of signals? And one of the things that came to mind was, what if we took some very powerful semantic features like you might find in a visual foundation model, and it brought them up into the 4D representation. And the reason we wanted to do this is even if we have a static dynamic decomposition, we don't know what those objects are. We just know these things are moving, these things are not moving. And so when we did this, we basically just added this extra signal to the output. And then when we were rendering the frames again, we kind of saw these, I mean, maybe it looks like we succeeded, right? But we also saw these like very strange patterns on the image. And so we were like, okay, some bug clearly or something like that. But after, poring over our code, actually, this isn't something that's, let's say like a problem with our, reconstruction, but it's actually something that we found comes from the positional embeddings that are used in many of these vision transformers, like DynoV2, like many other works. And so this was kind of, a little bit of a non-starter to us in terms of bringing these semantic features, because if you're going to have these blobs, completely ruining your understanding of the semantics, then you can't really use them. And so we then were thinking, okay, we kind of have this method that is able to disambiguate, 3D stuff from 4D stuff. Why don't we just try and disambiguate 2D stuff now? Because these artifacts are not really moving across time. And so, you can, very similar to what we did with the original architecture, we can now also just try and learn, let's say like a 2D artifact mask that is trying to actually learn these positional embedding artifacts, and then we can decompose the scenario. And here I'm actually visualizing what that looks like. So on the very bottom, you can see these artifacts. And on the second last row, you can see the video without these artifacts. So you can just see the semantic features actually in the re-rendered in the world. Now, like I said before, this is a 4D representation, right? So we're actually lifting these 2D features into space-time. And what that allows us to do is actually have just out of the box, a very, very, very strong semantic understanding of the world. So here, again, even without any labeling, if I just do a PCA on those features, I'm able to see, okay, all cars are generally in this cyan. Buildings are generally magenta. The road infrastructure and signage is generally green. And, I don't just have to do this for DynoV2, but we can also do this for models like CLIP, which basically trying to learn a correspondence between text and image data. And what's interesting is, okay, we can do the same decomposition and lifting and et cetera. And then you can query, okay, if I want to see a car, which features in the world most closely correspond with the car? And it's quite nice kind of how, now you suddenly in hand have an auto labeling tool, right? Just as a result of bringing these semantic features up into 4D. And of course, we don't just have to do this for something like car. We can do this for traffic signs or traffic lights. The flickering here is because I didn't do normalization correctly, so my bad. But the core idea is that now you have this very strong auto labeling capability. And with this auto labeling capability, you can also track objects of the same class over time. And so now you also even have an auto tracker that you can actually run offline on your sequences, which is semantically informed and very useful in this manner as well from Boris. So, as a result of doing this research, one thing that we noticed was, and then one thing that I keep telling, obviously I don't tell you guys this, but when I tell students or whenever I give these talks, now is really a fantastic time for you to do research. There are thousands of hours of publicly available data. Unfortunately, they all happen to be in their own unique formats. So working with Waymo is very different than working with UPlan, which is very different than working with Lyft, which is very different than working with FreeBSD Drive 100K or something like that. And so you kind of have this really annoying problem. And I'm sure you guys have probably fixed this internally by having your own unified data. But one more. Oh, there you go. One more additional format. Perfect, exactly. And so, yeah, this is actually something that I presented just at the tail end of last year at NeurIPS, which is a within the group we're now using, and we've open sourced our unified data format, and we've actually converted the 8 most common public data sets into this format and released all of this code for others to use. So again, I don't have to tell you guys all of this because I think you already deeply understand this pain point. But if it's of interest to you, or maybe you want to use some visualization code or something, by all means, it's all Apache 2 licensed. And stepping back a bit more broadly, our group, I just talked about 2 components of let's say what the group researches, which is novel end-to-end driving architectures and how we can use foundation models and maybe combine them with sensor resimulation. But the group really focuses on 4 key pillars research, which is the first one I said, novel AV architectures, the use of foundation models for AV use cases, of course, simulation, and then safety. If you have these learning-based systems, you really also have to assure that they're safe in the real world. So I didn't talk, of course, about many of these, but we have works all along this direction. And if you're interested, of course, take a look at our website. So yeah, in conclusion, I think the core points that I want to bring up are that for especially open loop planning, if that's all you're looking at, you really don't need much. You don't need very powerful architectures. You don't need crazy amounts of connections within your end-to-end AV stack. You can really just have a parallel AV architecture, which already can outperform just from those bird's eye view features many other existing works. And as I mentioned earlier, you really kind of want to have closed loop evaluation and especially closed loop simulation as a result of that to develop your AVs, test them, and evaluate them. And at the group and even myself, I think that having this kind of data-driven capability to resimulate environments and test within them is going to be really a key enabling factor for AV development going forward. And yeah, as a last little plug to our recent work on unified data sets, working with multiple trajectory data sets has now never been easier, hopefully. So yeah, thank you all very much for your patience and attendance. And I want to, if you have any more interest in our papers or code, it's all available here.
Okay, let's thank speaker. Thank you very much for your insights, talk. What about sorry, just a very short question about this multiple AV trajectory dataset conversion tool. What about use cases when we have multiple features that exist, for example, in some data set and they do not exist in another?
Yep.
Do you have some masking out? What?
Yes.
How do you deal with it?
Yes. I focused on, a map is a good example, right? Vectorized maps, you have a hilarious amount of variance between different data sets. So in developing this, we basically started by forming what is let's call it the floor of what everyone has. And this effectively ends up being almost everyone will have something like lanes, or let's call them road lanes, road areas, which could, let's say, include parking or something like that next to the street, pedestrian crosswalks and pedestrian sidewalks. These, let's say, 4 map elements you will find in every single data set. We also support traffic lights, but some data sets have them, some data sets don't. So it's basically, we definitely support the base minimum. And then if different data sets have more information, we would basically present that to you if you're using the data set. But if you're not, it would just show up as none or empty or something like that. So yeah, we chose to do standardization via the floor minimum that every data set provides.
What if you need some specific features, like map features from, I don't know, from new plan or from new scenes? It can be included. Yeah.
So the good thing is here, even if, let's say, it's not in these floor minimum, I don't know, 4 or 5 elements that we included, all of the converters that we use are also released with the code. So if you want to add, let's say, oh, I just want this 1 extra feature, I just want these 2 extra things, you can also add that into the existing converter.
Okay. Yes. Brian, can you ask by voice?
Yeah, thanks for the presentation. It's pretty cool. I had a naive question about evaluation results on open data sets. And how does it correspond to the eval results on larger scale industry level data? For example, NVIDIA's in-house data, if you can share anything.
Yep. Yeah, that's a good question. So basically, it's all going to depend on your how close your driving distribution matches, let's say, the open data set of choice. So, well, that's one thing, is let's say when I say driving distribution, I'm referring to, for example, the behavior that's observed, the kinds of the kinds of road layouts that are contained. But I'm also, it depends on how similar your, for example, camera resolution is, or the other kinds of sensors that you're using, and what your model is using. So lots of caveats here, but what I basically want to say is it depends, but I think in our experience, typically industrial data sets, and I presume this is also true for you guys, and you've probably seen this too, but typically the internal data sets used in industry are going to be of a higher quality than what you'll find in the public domain. And the reason I say this is because something like new scenes, right? 2019, the image resolution is 1600 by 900. I think nowadays you might find a little bit higher resolution. You might find something that's a bit faster than 2 hertz or 10 hertz, or so, or the LiDAR, right? It's not going to be 32 beam. It might be 64 or 128 or whatever, right? It might be a little bit larger. So what I would say is it's in the ballpark in terms of if you train, let's say, some model on internal data and you bring it into, for benchmarking purposes, I don't know, the new scenes data set or Waymo or something like that, you will be within the ballpark of what state-of-the-art methods, let's say on prediction performance or something like that will be, but you will not be the best. And that's because typically you're not implementing, right, like let's say Waymo specific things or new scene specific things to get to the top of the leaderboard. So we don't, we loosely look at these kinds of open benchmarks, but, and again, I'm in research, so we only use open benchmarks, but in the product side of things, I think maybe they look every now and then, but really they're focused on what's the performance on internal data with the set of sensors we have, with the compute requirements we have, and et cetera. So long-winded answer, but I think there's basically a decent gap between the data sets. But if you are to bring one model over and compare, I think you'll be within, if I had to guess, 20% or 10%, probably 20% of like the best performing public, open source model that's specifically tailored for that data set.
Thank you.
We also have the question. Sorry, Brian, is it all from your side?
Yeah, I just want to say thank you, Boris. That totally makes sense. Yeah, appreciate it.
Okay, we also have the question from Sean. Sorry, Sean. Yeah, Sean, will you be able to ask by yourself?
Yeah, I can just and I just wanted to add on to that point, like something like Waymo Open Data Set. I think the FOV is say 75 meters. I don't think it includes like very small objects like say cones or animals. So, for us, like we care about detecting these small objects up to say 105 meters. So as a result, that also kind of influences the BEV resolution we have to keep track of, and that also influences the architectures we can use. So, since we also care about like a much harder set of objects to detect, that also kind of influences the comparison with open benchmarks.
Yep, 100%. I mean, yeah, stuff like, that the megapixel resolution matters significantly in industry, and I don't think you see much discussion in the open side of things, because again, it's, they've chosen the format and they release it, and that's that, which is, perfectly fine.
Yeah, we also have the question from Sean. Nuro, Sean, will we be able to ask by voice?
Oh, do you want me to just read the question? Okay.
Yeah.
All right, I'll just read my question. I was just curious on early on, you were mentioning that like new scenes had like 97% of like straight driving, which wasn't very interesting. And then you were mentioning that, if you cut down to 5% of the interesting scenes, you started to see some interesting differences between the UniEd and some of those other models. And I'm just curious, like, do you think that's enough data to make an accurate comparison, given that new scenes, if I'm looking at the website, is 15 hours of driving? So is that 0.75 hours of driving we're comparing in that?
Oh, it's even less. I think it's 5.5 hours of driving data.
Oh, okay. And then and then I guess the follow-up was like when we were looking at the one of the follow-up slides also had like a comparison of collision rates in one of the graphs of like 0.4 to 0.1%. Was that on the interesting only scenes or all scenes?
So yeah, if you could see the screen now. So on the top row here, this is the full validation set. So this is, I believe this is, they've selected 150 scenes of their entire data set, which is, what is it, 15% of their data set. So the collision rates that you see on the top left are on the full, including straight driving, including scenarios where there's nothing around you. And then on the bottom is the specific targeted evaluation on this smaller subset where you are not only driving straight. So yeah, towards your question, is it representative? I mean, probably not for real world use, that's for sure. But it's kind of, if you only have a bag of models that were trained on new scenes and evaluated on new scenes, then this is kind of all you can do with those in hand. But yeah, it's really, we want close-up evaluation here. We really want to put these models into, to actually drive with their own output actually being effectual and not just on rails. So yeah, like I mentioned, I would view these as our first step in this direction, but not the last step.
Got it. Makes sense. Thanks.
Thank you.
I guess I had a quick question. Do you guys have any, and you guys probably know a bit about this, but you guys specifically like have any plans to like try and develop like open closed loop benchmarks? I think I've seen a couple papers like this, but like, I don't know, just curious.
We're working on it.
Okay.
Yeah, I mean, because these kinds of things hamper us too, right? If we can't evaluate and compare, like if everyone can't evaluate and compare, then you're going to have this, everyone has to choose, let's say, open loop benchmarks or something like that. So, stay tuned. Dharmesh?
No, thanks for the really great talk. I had a question regarding immersive nerve work. I'm curious how much creativity it actually has in terms of how much out of distribution scenes you are able to generate more complex scenario. I see like the result that you presented, the temporal and spatial aspect are both there, but does that move independently? Say, can we say a car moves instead of the entire flow, right?
Yeah, this is a great question. And so we are actually, I would highly recommend you watch the GTC keynote coming up in a few weeks, where we're very much interested in not just, as you said, not just having this capability of doing sensor simulation, but our group has done, I wonder if I can actually show this here. So our group has actually done, does that work? Oh, I guess it doesn't say it. Oh, it works. Oh, look at that. So our group actually has done a lot of research in traffic simulation as well. And I mean, I didn't talk about it today, but towards your question, one of the big areas of interest for us is taking this sensor simulation capability and this traffic simulation capability and actually having both of them running. And so, we also want to have the capability of, putting a car into some, very high fidelity, sensible world, but then also having other vehicles moving, not just in a replay capacity. So the reason I said, stay tuned for GTC and that week is because there's a good amount of work in this direction. And yeah, I think some of it will be on Showcase in what is it, a month's time.
Thanks a lot. Looking forward to that.
Seems kind of like you guys want to do like a Wabi world with no labels plus like better like closed loop simulation capability.
Yeah, I mean, I think for us, like, it's exactly like, having hyperboundary closed loop simulation, both from a sensor perspective and let's say agent behavior perspective, is kind of one of like the holy grail problems of autonomous driving. So NVIDIA has, I don't know how much you guys are familiar with NVIDIA different products, but there exists, NVIDIA has Drive Sim, which is kind of its large product for doing photorealistic simulation, and they have tons of effort being put into exactly realizing this vision. So yeah, I mean, we're very much working to, like I said, bring those two together, have this capability to do, as realistic as we can, closed loop simulation, which hopefully then gets better over time.
So small question from my side, again, about this conversion to data sets. Have you been able to to combine the data set and to train the new model on top of the data set? Because it's probably was one of the increased goals.
Yeah, this is the whole reason I made this was actually in support of another research project. Yes, yeah. So the reason this actually was born is because in 2022 I was working on a geographic generalization approach. I should say it was a meta-learning approach for behavior prediction, where I wanted to demonstrate the capability of basically generalization in two respects. One is going from one geography to another, and then the other one is going from one data set to another, with very different data frequencies and stuff like this. And yeah, but actually, I was writing this to actually help me do this, but I knew I needed, it was going to be a hassle otherwise to work with all these data sets. And yeah, actually that was the result of that paper was published in ICRA 2023. And then this, after pardoning it a little bit and having some other feature requests from members of the team and outside the team, then it was kind of like, okay, this is now, this tool is bigger than just one part of it. But yeah, absolutely. That was actually the first reason why this was created.
It helps.
Well, yeah, it was like now, I mean, I don't have an example here, but in code, I just specified with a string, lift trained, comma, new scene string. And then it subclasses the PyTorch dataset object. And so just like that, I'm now able to load batches of data from multiple different data sets. There's time step interpolation inside it. So I don't know, new scenes is at 2 Hertz, but lift is at 10 Hertz, or new plan is at 10 Hertz. I can synchronize those. So yeah, all of these kinds of utilities are in there, and yep, just openly available.
Yeah, just curious, usually because different data sets have different distributions a little bit, and it's at least in advance, it's not clear whether, for example, adding to Waymo open data sets, for example, new scenes would help on Waymo eval.
Yeah, I mean, there's like the typical, more data is generally better. But yeah, I think you're right. Basically, actually, in this paper, part of this paper was not just the tool itself, but we also did some data set to data set comparisons. And yeah, I mean, basically, Waymo is quite strong in terms of its diversity of what you get. But there's also other things, right? Because a lot of these data sets are collected from a vehicle's sensors. And so, you might have a little bit problems like, even with an excellent auto labeling pipeline, you still might have some weird flickering stuff or errant rotations. And we also compared to data sets that were collected from a drone. As you can imagine, the accuracy, let's say, of the bounding box is like fantastic by comparison. Not to say that we should now switch everything to drones, but more, it gives a good kind of upper bound on, right, just like the difference in terms of like, a fantastic auto labeling pipeline or fantastic public auto labeling pipeline with, perspective to bird's eye view as one example. But yeah, adding, new scenes to Waymo, I'm not going to give you that much, except for maybe the left driving, because Waymo doesn't have left-handed driving.
Thanks. Alex, do you have any other questions to our speaker? Okay.
Cool.
Let's thank speaking one.
Thank you, everyone.